Hello. So this is our project. For our project, we focus on building a flight delay predictor using real US flight data. This project was completed by Tommy Pham, Ewan Green, and Clark Smith. So the main idea behind this was to explore how data mining techniques can be applied to a real-world problem, which affects millions of passengers every year. Flight delays are something almost everyone has experienced when flying, but those delays give us a large amount of data that is publicly available for us to analyze. In this presentation, I'll walk over our motivation, dataset, pre-processing steps, and three different models we implemented, and finally, how we put it all together for a working graphical user interface. So, motivation. Why study flight delays? Flight delays are not just an inconvenience for passengers, they are also extremely costly for airlines. According to Airlines for America, delays cost airlines billions of dollars each year due to how much the fuel burning, the crew overtime, misconnections, and lastly, customers' dissatisfaction or distress on getting with the airline again. So, from a data mining perspective, flight delay is also interesting because there's a large publicly available data set everywhere of on flight information over many years. And this makes it good to apply different data mining techniques like clustering, classification, and regression on it. So overall goal is to build models that can analyze these delay patterns and provide us with useful predictions, especially information that passengers would use before a flight depart to see how much a flight will be delayed by. So, for the project overview, we work with a US flight data from Kaggle from 2018 to 2023, and we applied three different machine learning data mining techniques on this. So first is clustering, where we would group flights with similar delay patterns together. And then second is classification, where we would predict whether a flight is delayed or not by 15 minutes. So if it's less than 15 minutes, the classification will say it is not delayed. And thirdly, regression, which will predict the exact delay minutes. And then finally, putting it all together, we make a Python GUI that allows users to input their own flight information and see predictions from all three models in one place. So again, going back over our data set, we got our data set from Kaggle called Flight Delay Datasets from the year 2018 to 2023. There were a total of 16 features, but we only used 10 because these are the only information that was available to flyers before the flight, which was year, day of month, the flight date, airline, the origin city, where they're going, the CRS, the departure time, the arrival time, and the taxi out. And and yeah, these features were more valuable to users because they had it before the departure. So for the pre-processing steps, before training the models, we first converted the flight dates into a numerical format so they could be used by the model. Second, we encoded the categorical features to numbers like the airline, origin, and destination. And then thirdly, we standardized the numerical features so they had a mean of 0 and a variance of 1. This is important for the gradient-based algorithms. And then finally, we do a 80% training set and a 20% test set to evaluate performance on unseen data. So our first model, we implemented ourselves something kind of similar to the mini batch k-means library, but we did it a bit differently. So we chose this because it was more efficient for the larger data set since the regular clustering was running a bit too long when we first did it. So the output of this model it would have six clusters and a batch size of 10,000, and and it would output a cluster assignment for each flight as well as the average arrival time for each cluster, which gives us like a summary of the typical like the delay behavior for them. This is what the pseudocode looks like. This algorithm starts by randomly initializing each cluster, and then for each iteration, it samples a batch of data points, computes the distance to each centroid, and then assign the points to the closest cluster. And then these centroids are updated incrementally using a learning rate depending on how many points has been assigned to each cluster. This makes it a good like average, give us a good average k-means behavior. And then the final output is a set of cluster centroids and cluster assignments. So for our results, most clusters showed a mean delay around 13 to 15 minutes, which is like average, like the average delay. And then some of the clusters were more associated with more specific airlines. But overall, with the cluster results, it performed the best on moderate delay. So if a flight was delayed by 15 minutes, you would get a prediction maybe like 13 or 17. But it was less accurate for the more extreme delays. So if it was more than over 30 minutes, or if it was just like no delay at all, it would output like for 30 minutes, it might output something like 50 minutes instead. Or if there was no delay at all, it would say that would be delayed by 14 minutes. This is partially because since the clusters were give you like a more average result, it can't work with like the more extreme delays. So for Model 2, which was logistic regression for classification, we would predict whether a flight is delayed or not based on 15 minutes. If it was over, then it was delayed. If it was not, it was on time. We used a gradient descent plus L2 regularization, and then we output the sigmoid function probability score for the delay. So this is the pseudocode. After pre-processing the data, we we initialize the weights and repeatedly update them using gradient descent. At each step, we compute the predicted probabilities using the sigmoid function, and we calculate the gradient of the loss with respect to the weight. And then the L2 regularization is included to penalize like large weights, which helps improve the overall generalization. After training, the model can output the probability that a given flight will be delayed based on the sigmoid function score. So for the results, we achieved around a 79 to 81% accuracy on the test set. The For the prediction, it was pretty similar to clustering. It had good performance on moderate delay. One like if it was delayed between 1 to 20 minutes, it will only be off by one or two. But again, it was less accurate for the more extreme delays. We guess that this could be like because the overlapping of features, which affect the classified accuracy, and again the features weren't very linear to each other, which leads to our last um, the model, which was linear regression, and we used that to predict the exact delay minutes. Um, the goal here was to use regression as like a simple model to see how it would perform on the data, even though like a lot of features were linear. We trained the model using like standardized features, and then we tested by using the mean square error with gradient descent. So for the pseudocode, nothing too complicated. After pre-processing and splitting the data, we initialize the weight, and then we repeatedly compute the predictions, errors, and gradient. The weight updated at each step until it converges, and then at the end, the predictions are returned in like the actual like minutes. For the results, it wasn't great. The MSE score was 2500 to 2600 minutes square, meaning that it can be off by like 50 minutes or so. But it was still a decent accuracy for again the 1 to 20 minute mark. But it wasn't as great as compared to the other. It still struggled on extreme delay, and obviously this shows the limitation based on some of the papers we read of linear models on non-linear data features. Finally, we have the GUI design. So we used the Python tkinter thing to make it. Again, the user would just input the 10 features that we chosen. For the background pipeline, it would parse the input, apply the same pre-processing step as in the training for the three models, run the three models, and then finally they would click the output and it would show the cluster ID and mean delay for clustering, the probability of delay for the classification, and predicting the delay minutes for the linear regression. And again, we'll show this in the demo, but this is what it looks like. You would input like all these things. So this is like one example flight from the data set in 2020. And then you can see here it outputs the clustering and then the clustering characteristic, logistic regression, linear regression. The estimate delay here was 14 minutes, which was only off by like a minute or so, which from the actual delay. And then finally, this is our file structure. We had three different, everything is in the data mining project. We had the clustering algorithm folder, which had the two Python file for training a clustering, and then same with classification regression. The flight delay data set would be outside of these folder, and then finally we would have the GUI along with the theme folder and the Azure.tcl, which we use to make it, like make the theme. So in conclusion, clustering had a moderate prediction accuracy. Logistic regression didn't perform too bad with 80% accuracy, and linear regression was able to capture the average trend, but again, it wasn't great because the features weren't very linear. But I think this project showed that data mining techniques can be used to solve real-world problems like flight delay. And then for our future work, we plan on perhaps using more advanced machine learning models, like maybe like neural networks or random forests. Because again, linear regression, logistic regression might not be the best for the features with the features that we were given. And to improve the GUI, we would have more visual feedbacks, like a graph of comparison between the models and other things. And now on to the demo.
Hello, Professor. I hope you enjoyed the lovely read-off that Tommy just gave. Now we are going to journey over to our code, which we have right here. You can see it mirrors the file setup that we had seen earlier. We have the classifier algorithm, we have the clustering algorithm, we have the regression algorithm, and then we have all of the joblib files that are generated, basically the model that we built out of these files. So what we're going to do now is we are going to actually run the GUI. It should take a little bit to run just because it's dealing with some of the training data and messing around. But once it finishes, our beautiful GUI that we have designed will pop out or pop up, and I will demo it for you. So bear with us for a minute while it boots up. Okay, welcome back. This is after the code is finally finished running. So we have our GUI, which has popped up here. You can see the Azure.tcl. This is the visual accent that we're using in order to supply the GUI with something a little bit more stimulating to the eye and easier to work with. It's a pretty simple file that uses this and some light mode information as well. All of it should be located in the theme. It's not in there right now, but the information or the relative folder is very easily imported from GitHub and results in all this. As you can see for the flight delay predictor, basically the methodology that we used, as explained very heavily in the paper, is that there were, I think, 16 or 17 features originally that we had the opportunity to work with, but some of those were directly indicative of the actual delay that we would get as output. So because of that, we chose to use the features that we thought were possible basically for the user or for anyone who wanted to realistically use this to predict flight delay would have prior to the flight as opposed to after. So some of the features obviously that we avoided adding in were the actual flight delay itself, as well as stuff like actual arrival time, because if you have the actual arrival time, then um, it makes it a little bit more difficult in order to function. But yeah, basically, with all of that in mind, um, this flight delay predictor can feasibly run, and that's what we're going to do right here. So you see we press the button, and we have the k-means clustering accompanied by a cluster right there, the estimated delay, for the cluster. So this obviously the clustering is not necessarily meant to predict delay time, but it's still an important characteristic because we can see inside of each individual cluster what the averages are. In this case, I believe it was 14.3, yeah, shown right here. And then we have the cluster characteristics. Obviously, I found that just saying a clustering number doesn't actually mean anything from a user perspective because clusters are indicative of actual patterns as opposed to just being a pattern. So obviously saying cluster 4 doesn't actually mean anything. So we have to show the key characteristics that are present within the cluster. So obviously we see the average departure time, the CRS departure time, we have the taxi out, we have origins and destinations as well as the airlines. So with all of this, we can actually get a formulation of what the cluster actually represents. So from Chicago, Atlanta, Dallas to places like Chicago or Dallas or Denver. So that's the more representative of what this cluster is basically. And then on here we have the logistic regression basis. So you can see the delay says greater than or equal to 15 minutes. So that was their baseline that we gave for classification of delay basically. If it's greater than 15 minutes, it's considered to be an actual real delay. If it's less than 15 minutes, then it's not actually a delay. But the probability was 0.209, so very, very low delay chance, which means that the predicted for the logistic regression at least said no. And then our linear regression, which tends to aim a little bit high, the predicted arrival delay that it gave was 15.18 minutes. Obviously, that's a little counterintuitive to the time given by the logistic regression, but the idea of having so many different methods available is that you can kind of use a conglomeration of multiple different results in order to produce um, basically whatever you want for your output, or at least to get a better larger picture of whatever the true output actually is. Obviously, you can go in and these statistics can be manually changed. So if we wanted to use a different city and say we were flying from somewhere else to somewhere else, it would be just as easy. In fact, I'll do that right now. So we can paste in here something like Denver CO, and we can change the departure time, we can change the flight date, all stuff like that. It's all completely possible. Um, we can change the year, all of this, um, and then make predictions off of that. Um, Obviously, in this case, or chance, I didn't actually change very much, so hardly anything changes. We stay within the what's it called zone. But yeah, basically, this is the format and the methodology that we use in order to create the flight delay predictor. Um, yeah, that's it. Thank you very much.